Just a little warm up today. I'm going to get started, but we'll talk about it a little more. All right, so last class, we left off talking about first and second derivatives and when they're positive, negative, zero, increasing, decreasing, what that means. So let's take a look at an example for a different polynomial. Take a look at this j of x. You can find its first and second derivatives and think about where each of those are equal to 0, and thus around that, where they're each positive and negative, and think about what that tells us about function j. So there's a variety of different things we can look at to analyze the behavior of j, other than just graph it on a calculator and see, or plug in a million different numbers and check. But some of those involve first and second derivatives. For a lot of applications, the structure of the functions isn't necessarily very complex. It's usually just things like coefficients or multipliers, exponent coefficients, things like that, that are unpleasant numbers in order to match data, or in order to meet specific things. Sometimes the zeros of these functions are irrational or something unpleasant at least. But if I want to know something about this function j of x, I could obviously plug in a whole bunch of numbers for x and c. I could use a graphing calculator and see, but there's some things you can do pretty quickly just with the first and second derivatives that would tell you a lot about it. So the first derivative, again, tells you about rate of change. And so if the first derivative is positive, that tells you that j of x is increasing. If the first derivative is negative, that tells you that j is decreasing. If the first derivative is 0, that's an opportunity for it to be changing from one of those to the other. It doesn't necessarily do so. It could just be a pause where it continues on the same way it was going before. But if I know all the spots where the derivative is 0, and this, as a polynomial, this derivative isn't going to be undefined anywhere. There's no radicals or anything that has a limited domain. There's no denominators and so forth. But if I want to know when this equals 0, not its value at 0, that might be of interest, but if I want to know when this equals 0, you could use the quadratic formula, or this one's actually factorable. I'm just going to swap the order around. Negative 3x squared plus 18x minus 15, factorable with nice integer numbers. If you factor this out, let's see, minus 6x plus 5, you can see exactly where this is equal to 0 pretty easily. And then in between and around those zeros is where it would be positive or negative. So I can see that the derivative is 0 at x equals 5 and x equals 1. So j prime of x, I'm just going to write it as a sentence, equals 0, kind of as a sentence, at x equals 5 and at x equals 1. Every place else it's either positive or negative. And so if you wanted to take a look and see what it is where, you can do the old, like the algebra trick or trig pre-calc trick of, well, let's see, here's 1 and here's 5. So I'll list x values of 1 and 5 here. X equals 1 and 5. J prime of x, I know is equal to 0 at those two spots. In between, like from negative infinity to 1, between 1 and 5, and beyond 5, we can check to see what's going on with j prime of x. And within each of those intervals, since those are the only zeros of j prime of x, within each of those intervals, as it's continuous, it's only going to be positive or negative within one interval. So, for instance, if I test x equals 2, which is something in this interval, into j prime of x, I can do it up here, or maybe easier here. You can see if x equals 2, I've got a negative times a positive, which is something positive. So I can say that, oh, not only at x equals 2, but every x value between 1 and 5, j prime of x is positive, or j of x is increasing. Great. We could also pick numbers like below 1 or above 5. I'm just going to pick some convenient close by integers. But at x equals 0, j prime of x would be, let's see, negative 3 times negative 5 times negative 1. That's 3 negatives multiplied together. Regardless of the exact number value, it's something negative. And if I pick something larger than 6, I'm going to have a negative times 2 positives. So, or larger than 5, like for instance 6. So that's going to be negative also. So I could say that based on these signs of j of x, or j prime of x, that j of x is decreasing, then increasing, and then decreasing in those three intervals. So decreasing, increasing, decreasing. So it's that sort of pattern, which should maybe not be surprising based on the fact that this is a cubic polynomial with a negative coefficient on the x cubed term. Right end goes down, left end goes up, and it goes like that. Only we know it's a polynomial, so it's not actually corners, it's curved. And using the second derivative, we can even figure out where the curvature changes. But based on this, just the first derivative, I can say, oh, well, this spot here at x equals 1, where it changes from a negative first derivative to a positive first derivative, otherwise known as j of x changes from decreasing to increasing, I've got a minimum in my graph that occurs at x equals 1. And I've got a maximum in my graph, local maximum, meaning it's the top of the hill, that occurs at x equals 5. Now the ends, obviously this end, polynomial-wise, we know goes up, up, up. This one goes down, down, down. So those aren't the overall, there's no like largest x value or largest y value or largest x value, let's see, largest or smallest y values in this. There's values that are minimums or maximums. And in terms of most applications, there's generally a fixed domain that we're interested in. It's not all x values from negative infinity to positive infinity. If we're working with constructing some sort of figure and using pieces of material, they can't be infinity feet long, and certainly maybe not even anything negative, let alone negative infinity. So there's usually some sort of restrictions that mean that these points that aren't necessarily the highest or lowest overall could end up being something of use or the thing that we're looking for after all. And we're going to look at some examples, some specific examples today, not just generally me saying we're building something and this is biggest, but we'll look at some specific functions today that we're going to try to optimize, find a maximum or a minimum based on some specific constraints, some rules to follow, and some pieces of information that combine to help us put together a function that describes how we obtain these values, such as costs or profits or whatever volumes, whatever it might be. All right, but in any case, just from the first derivative and substituting in a couple of values, we can see what's going on. But you can also look at the second derivative, which is really simple. It's a linear function. I can see that the second derivative equals 0 at x equals 3, maybe even just by looking at it. But j prime prime of x equals 0 at x equals 3, otherwise known as j prime prime of 3 equals 0. But again, the second derivative tells me how the first derivative changes. And I can see that maybe even looking at this. X equals 3 is the spot where this equals 0. It's a linear function. If x is anything greater than 3, this will be negative. If x is anything less than 3, this will be positive. So it's a nice simple function to look at. Don't even have to maybe think about a whole number line and substituting in, but I'll write it in number line format anyway. If I have x values on either side of 3, like 2 or 4, if I'm looking at the second derivative, if x is 2, or in fact anything less than 3, I'm going to get a positive value of my second derivative, and it's going to be negative afterward. Now, second derivatives tell me what's going on with my first derivative the same way that first derivative tells me what goes on with my function. So I could say, oh, my first derivative increases everywhere up through x equals 3. And then my first derivative decreases everywhere after x equals 3. I didn't write down the specific values here, but if we work them out, this middle part, there's a couple of things going on, but my first derivative increases and then decreases. If I look at this graph, the way I drew it was with straight lines, so I've got a negative, then a positive, and then a negative. I know that my first derivative is increasing all the time. So that means whatever negative value it might have, it becomes less negative and less negative till it hits 0, the derivative value that is, and then can increase into the low positives and higher positives. And so in reality, what I've got is not a straight line with the same negative derivative all the time, but a negative derivative that's becoming less negative and then hits 0 and becomes positive even. I know it actually hits 0 at x equals 1. It's not the sharp corner there. I know that it's got to be something kind of curved here where a tangent line or a line that goes through two very close points right near x equals 0 would have a steepness or a slope of approximately 0. I'd have negatives changing into 0, not suddenly jumping to positives, and then going upward. But then once I pass x equals 3, my derivative stops getting larger and starts getting smaller, or shape-wise, the curvature changes. That second derivative, visually speaking, refers to the curvature of graphs that are not straight lines. So a positive curvature is concave up, is what it's called, is like the left half of that. So positive second derivative, kind of like a smile in this case. So positive smile, negative frown. So we've got this curves down for negative second derivatives, but that could be any part of it curves down. It doesn't have to be up and over the top of a hill, but just anything where as I go to the right, the curvature, the steepness lowers, whether it's from a positive to something less positive or a negative to something more negative, which is a decrease, or if it's something from 0 to a negative, any of those are a decrease in a derivative value. So in any case, our shape we can kind of put together from lots of clues. Decreases, then increases, then decreases again, where the changes in increase to decrease are a minimum and a maximum at x equals 1 and x equals 5 respectively, and at x equals 3, there's a change in curvature. So this is the straight line simple version of kind of what's going on, but piecing it together, we can say, oh, we've got a graph that goes like this. Now I didn't work out any y values, but a change in curvature, which is kind of harder to pin down visually than a top or bottom of a hill is, but this change in curvature occurs at x equals 3. There's a maximum at x equals 5 and a minimum at x equals 1 in this graph, all just based on looking at the derivative. So we could find y values by substituting into the original j function if we wanted to plot this by hand. I mean, that's more useful for like something. If you want a really nice graph of this, grab a calculator. But if you just want to know where is it increasing versus decreasing, or where does this change over, sometimes better than just looking at a graph and guessing is being able to narrow these down precisely using calculus. Because at a point like this top of the hill here, I'd have to have a derivative of 0 and a changeover from a first derivative positive to a first derivative negative. Or you could also think of that as it would have to be at a spot where I've got a negative second derivative and a first derivative of 0. Similarly, at this minimum here, I'd have to have from left to right something changing from decreasing to increasing, so a negative derivative changing to a positive derivative, first derivative. Meanwhile, the second derivative would have to be positive the whole time. So there's lots of ways you can kind of mix and match uses of the first and second derivatives along with function values, but you can get a general shape of the graph without knowing any y values whatsoever, without having to worry about specific values of j of x, which is less pleasant to substitute into mentally or with a calculator, either one. It just takes longer to plot. But regardless, we can get a graph of that. And if you want to double check your calculus work while you're working on these sorts of things, maybe for first times or something, if I can get this to hi. Let's see. Here we go. Here's j of x. 2 minus 15x plus 9x squared minus x cubed. If we look at a graph of y equals j of x, looks kind of as expected. We can see what the y values are in this graph, but you can verify, yep, there's this bottom of a hill that seems to occur at 1. Now, looking at it visually, all you can really do looking at a graph is estimate. And I can click on this and see coordinates like that, but sometimes it's hard to get exact values, and it's also, it doesn't tell you when you hit the highest or the lowest, so you just hope that you saw it. But in any case, scrolling across this, I can say, oh, well, this looks like 5. Yep, 5's that maximum, and you can see in the corner there it says the y coordinate corresponding is 27. 1 is this locally minimum spot. Ooh, I almost had it. At y equals negative 5. And what you can't really see on here is that there's no way to verify this, but just looking visually at this, I can see, well, it looks like if I put that cursor there at x equals 3, or close to x equals 3, to the left of it, it does look curved up, and to the right, I can see that curved down. So that seems like a reasonable spot to have this, what's called an inflection point. Again, that's where the curvature changes, but that's where the second derivative is 0. So you can have second derivatives and first derivatives equal 0 in the same place. Those are just those super flat spots where, depending on what all else happens, it might be just a plateau on the way down. It might actually end up to be a maximum or minimum. Zeros are kind of, you have to investigate a little bit more, but they are points of interest in any case. Those are the only sorts of spots where something cool could happen. So let's take a look at this thing. So we're going to be working on story problems related to what we just did with j of x. which are generally called optimization, to be most general about it. Talk about maximums or minimums, or maybe both. Usually in an applied situation, only one of the two is something you're looking for. You just generally don't want to maximize or minimize the volume, just one or the other. But with a function, various values of the independent quantity can be chosen, each resulting in a corresponding value of the dependent quantity. Okay, great. That's just facts about functions. If I pick an x value, I can find the corresponding y value. Or if I pick an independent value, I can find the corresponding dependent value. So to find the best value, optimizing our situation, we need to know a few things. We need to know, like, what do you mean by best? Because that on its own doesn't really make any sense for any individual situation. Excuse me. We need to know, well, what function is it that's going to provide us this thing that we're trying to find the best value for? I talked earlier about like a cost, maybe minimizing cost. I'd have to have a function that has as its output variable values of cost. Or if I were trying to minimize, let's see, maximize volume or something, I'd need to have a formula, a function that relates some sort of independent variables to how I calculate volume and give me an output value of volume, and then I could find a maximum of it. So I also need to, for the specific problem, determine what is it that I'm trying to do, maximize or minimize. Those are those like best sorts of cases. But also, I need to think about what sorts of independent variable values are sensible for the problem that I'm dealing with. Because unlike just, polynomials, domain is all real numbers. But for a situation that's being modeled by a polynomial, not necessarily are all real numbers something reasonable to use. Or are they sensible or possible? It kind of depends. So we have to think about a few different things. So if you were given the problem to move this out of the way, trying to find a maximum value of this function f, if I were only looking at the domain from 0 to 30, then just kind of visually estimating this, if I'm looking 0 to 30 trying to find the maximum value, that would be to about here. I can see the maximum happens way back at the beginning, toward like right around x equals 5 or 6, somewhere back in there. I'm trying to maximize if I have that domain. If I had a different domain though, although this is certainly the largest y value in the picture that I see here, if I'm not including this 5 or 6 value as a part of the domain, it can't be an answer to that question. If I'm looking, for instance, 10 to 35, like maybe I'm trying to construct something, the length, the smallest dimension has to be at least 10 inches long. So I'm not considering this. Well, starting at 10 and going over to 35, well, in that set of numbers, there's negatives, which doesn't really make sense with my finding a volume of something, random example, but between 10 and 35, the largest dependent value, the largest y value, actually happens at 10, which there's nothing special about 10 otherwise. It's not the top of a hill. It's just the beginning of our domain. And because we cut off the stuff prior to that, which was higher and contained previous maximums, because we've chopped that off, we're not paying attention to that, well, we just happen to get this endpoint as being something significant. In this case, it would be a maximum. Now, if I were looking for a minimum, that endpoint wouldn't be important. The 35 might be, though, because that's certainly the minimum. If I was looking from 14 to 24, 14's about here to 24, which is just before the top of that hill at F, where the F is. It's like right about here. If I'm just looking in that section, trying to find a maximum, well, it happens to be that right endpoint, that 24 would be the highest spot in that. But if I'm looking for minimums, everything changes. Like minimum 0 to 30, well, between 0 and 30, looks like the lowest value is maybe at 30. The endpoints are important. Sometimes they don't end up mattering, sometimes they do. It really just depends on the problem. But make sure you keep in mind, as we're going through these examples, that we're going to go through a few of them today, besides the hard part of this, which is setting up the function in the first place, like setting up what is the function f, and you don't have to graph it, but you certainly can. that usually takes most of the time of these optimization problems, because after that, what we're looking for is, well, where are the key points, the endpoints of the domain, because those could be something that's highest or lowest, as well as these maximums and minimums, which would only occur at places where the first derivative is 0, although not all places where the first derivative is 0 end up being important, just like not all endpoints end up being important. But those are the only sorts of spots we have to check. We don't have to check all infinitely many points within a domain. So the idea to find the best value of the dependent variable, you have to think about the list of the possible points, independent variables, that could be of use, which are, as I was just saying, the endpoints of the domain and the critical values of the first derivative. So we've been looking at kind of polynomial functions, which don't have any undefined derivatives, like sharp corners. So critical values include places where the first derivative is 0, but also places where the first derivative is undefined, but the function isn't. So like a sharp corner has no derivative, but it does have a function value. Because those could also be maximums and minimums, just sharp corners instead of smooth hills. So those critical values of the first derivative and the starting and ending values of the domain. So you have to make sure you think about the starting and ending values of domains so you don't skip over that. Lots of times they aren't important, but sometimes they are. It just, like I said, it really just varies. But in the end, here we go. Every optimization problem is about defining and using a function whose dependent variable is the quantity we're trying to maximize or minimize. So the key to all of this is starting out by making sure you understand what the function is if it's given to you that you're trying to maximize or minimize, or if you're not given a function, like if it's not a proprietary function of some sort, if it's a, oh, I need to describe this based on stuff I already know, like geometry or just general, like, I don't know, unit price times number of units sold, sort of revenue functions, something where you can just come up with it from some given information. We will see some geometry stuff. We'll do some trigonometry. You need to put together this function and then figure out where its maximal and minimal values are, or at least one of the two. So, as a first example, kind of a story problem, what two non-negative numbers a and b, whose sum is 25, maximize the value of 2a squared plus b squared? And then what values of a and b minimize the same thing? So in this case, we're kind of given the function. It's not quite in a usable format right now. But again, the goal is to write a function whose dependent quantity is the thing that we're trying to maximize or minimize. Now, we do want it to be a function of one variable, so one input variable only. So that's what our slight issue is right here. But we've got most of the structure right here. Like, oh, I'm trying to, well, first we'll do the maximize. We're trying to maximize 2a squared plus b squared. So let's see, I'll call it y equals 2a squared plus b squared. So as is, this has too many things in it. I can't graph this the way we just graph that function f and look for tops and bottoms of hills. But keep in mind, a and b here aren't independent variables. One depends on the other. Because if I told you the value of a, you would know the value of b, because we know some facts about them. A and b are non-negative, so 0 or bigger. And I know that a and b add up to 25, because it says so. So for instance, if I say, well, what if a is 2? Well, then you'd know that b is 23. They're not independent. They're related by this sum of 25 relationship. But since a and b are both non-negative, I can express either of these sorts of things in terms of, like, express one in terms of the other. So, for instance, instead of having a plus b equals 25, I could say, oh, well, b is 25 minus a. So I could write this as something in terms of one variable, 2a squared plus 25 minus a, quantity squared. Agreed that's equivalent based on the fact about a and b's relationship? So now this, I could write this like f of a equals something like this, now that it's all one variable if I want to use fancy function notation. It's a function of a, an independent variable, but if I know a, I can find b even though it's no longer involved directly. Let's see, I'll just leave this as 25 minus a squared instead of multiplying it out. But in terms of the domain, rules for a, well, it can't just be anything greater than or equal to 0, right? Because a and b, meaning a and 25 minus a, both have to be greater than or equal to 0. So a is restricted to what domain? It's between two numbers. 0 and 25. Because if a is any bigger than 25, there isn't a possible value for b, if you want to think of it that way. So I've got this function that I'm going to try to maximize, and we'll try to minimize it later, where a is between 0 and 25. And it can be either one of those, but it's just restricted to that interval. So if I want to find the maximum value of function f here on the domain 0 through 25, I could grab a graphing calculator, have it graph this, and look. I could get a good estimate that way. It's not probably going to be too hard to do using calculus, but what I'd be looking for is a place where you can see, again, this is a quadratic polynomial, so it can't be anything other than it's a parabola, right? So as long as that vertex is between 0 and 25, that vertex would be my maximum. You can even see it's going to be or minimum, actually. So I've got 2a squared and then 25 minus a squared. If I were to simplify that, that'd have an a squared, positive a squared. So if I'm looking for a maximum, it's not the vertex here. That'd be the minimum. But let's take a look at f prime to see where the, of a, to see where the derivative is 0. It should be a linear function. It's a little bit messy right now, but without doing a lot of algebra, I can say, okay, for a plus chain rule, 2 times that, all to the first power, and then times the derivative of the inside. 2 times 25 minus a to the first power times negative 1. Or, in other words, this whole thing is, let's see, negative 2 times 25 is negative 50. Negative 2 times negative a is, what do we have here? Let's see. Negative 2 times negative a is 2a, and then I've got a 4a, makes 6a. So f prime at a, in easier to look at linear form, is 6a minus 50. So it's positive, negative, or 0 at all places. It's never undefined. Although it's not a whole number, I can see where it's going to equal 0 by just doing 50 divided by 6. 6a minus 50 would equal 0 at what? 50 over 6 is 25 over 3. I'll just write it like that, 8 1/3. But the second derivative is 6, which is positive, meaning concave up everywhere, so this shape. So this 0, which is at 8 1/3, which is within our domain, is a minimum. The first question we're looking for here is actually, what's the maximum? Well, I've got endpoints, and based on symmetry of parabolas, 0 is closer to 8 1/3 than 25 is. So I'm guessing that the maximum is going to happen at a equals 25. But we can check. Here's our one critical value, 25 over 3, which maybe just, basic algebra-wise, oh, it's a parabola that opens up, so that's going to be a minimum because that's the vertex of it. But at x equals 0, I can figure out the y values. It'll be higher than this vertex, as will the value at x equals 25, or a equals, rather, 25. At a equals 25, f of a is going to be big. This part will be 0, but this part will be 625 times 2, 1250. So f of 25 is 1250. And back at 0, which is the other endpoint, f of 0, if I sub in a equals 0, this part's 0 and this part's 25 squared, so 625. Now, this value, I don't know what it's going to be. Less easy to do arithmetic. But all we'd have to do to figure out what is that minimum value, which is the second question, is substitute in a equals 25 over 3 to this, which I'd have, let's see, 625 over 9 times 2. Let's see, 1250 over 9 plus 50 over 3 squared. Let's see, 2500 over 9. So whatever on earth that is, 3750 over 9. Which is definitely smaller. It's around like 400 or something. 9 goes into 37 4 times and 150, whatever. So 400 and something is the minimum sum that we can get that follows these rules. And 600 ends up being nothing important. The value at one endpoint of the domain, the maximum happens at a equals 25. So in terms of answering this question, what two non-negative numbers, a and b, whose sum is 25, maximize this? Well, this just says, well, a is 25. All right, so a is 25 means b is 0, right? So a equals 25 and b equals 0 will maximize that sum. The value is 1250. A equals 0 and b equals 25 is nothing important, but it's something we checked. That's kind of an in-between. But a equals 25 over 3 and b equals 25 minus that, 50 over 3, would be the minimum sum. Or minimizes the sum. So those are the three pairs of numbers that we checked. We didn't have to check every other number. And note that it doesn't have to be whole numbers or integers that are solutions to these sorts of things either. So in terms of, oh, well, I'll just check all the numbers. It could be 0 and 25, 1 and 24, 3 and... You're missing infinitely many numbers if you do the guess and check just using whole numbers, although you might be able to narrow it down to near where this minimum or maximum might be just by following trends in the numbers and realizing it should be something quadratic. It can't be that like jumps up and down a million times. But in terms of answering this question, we found a function whose dependent variable is the quantity we're trying to optimize, maximize, and then minimize. And it was just a matter of taking the general structure and changing it into a function of one variable by realizing the relationship between the two letters that were used there. One depends on the other, in essence, because a plus b has to be 25, that extra rule at the beginning. It's a constraint, an extra rule that's given. But then the only places where we could find maximums or minimums are at these critical values. And again, it's endpoints and critical values of the domain. Sometimes endpoints are called critical values. It just kind of depends on what book you're reading. But check the endpoints, check where the derivative's 0, check where the derivative's undefined, although polynomials don't have that. And you can find all the points needed. You could also obviously graph. If I were to graph y equals this, I could see between 0 and 25 where the maximum and the minimum are. But we can algebraically, calculously prove that also, as opposed to just like relying on a graph that did all the work for us. You can kind of combine knowledge of calculus and graphs to help yourself also in some cases. If the numbers are really tedious, you can at least zoom in to figure out, okay, where are these supposed to be? and then find out what they are using graphing technology. All right, but let's take a look at a slightly more story problem-ish story problem, as opposed to just A's and B's adding to 25. So just make sure, as I say, read the whole problem before you worry about trying to write formulas. Sometimes there's a whole bunch of things described and you might not need to use the aspect of it that first struck you, like, oh, I'm going to use the Pythagorean theorem. Maybe you are, maybe you aren't. Maybe it's going to just be perimeter of a triangle. Don't overcomplicate things by jumping to conclusions. Read the whole problem, make sure you understand what's going on. And writing out a function that models that, that's usually takes the longest amount of time. The derivatives, honestly, at this point, they end up to be really simple things like quadratic or cubic functions, sometimes a small rational function, but they're not generally as complicated as a natural log of a square root of an exponential function plus a fraction or something. Those don't often just kind of come up from a described situation. So make sure you look at what are the quantities involved, including the units on them. Sometimes looking at the units can also help you determine what you're supposed to be doing. Determine the greatest number of square feet of something, something. Ooh, square feet, that sounds like area. Let me think about area. So look at the units and the quantities, and then think about when you do see numbers, some of them are a specific example of a number. Sometimes it could change to something else. Sometimes it's fixed for the whole problem. So make sure you read carefully. But goal, maximize or minimize the quantity. That's the dependent variable of a function, because we're looking to find the maximum or minimum y values is what we're looking at in those graphs. That's what we can do with calculus. So if you set up that dependent variable, the output, to be the thing that you want to maximize or minimize, then derivatives can help, and also graphing can help. So here's a story. I'll let you take a minute to read through the details of this, but a rectangular storage space. Diagram, since it's describing a building or a shape, that might be helpful so you can label parts. Again, so we've got a rectangular storage space that's going to be created against a building. We've got 84 feet of chain link fence that's going to surround the three sides that aren't the building. The building's wall forms the fourth side of the enclosure. And because of whatever we're storing in there probably, we can't make it narrower than 4 feet. So we're trying to figure out what dimensions we should use to maximize the area, while keeping in mind we've only got 84 feet of fence. So when you have something like this, kind of geometric in nature, we've got a rectangular storage space. Maybe imagine, drawing something, say, all right, here's my building. I'm going to make a rectangular enclosure, and these three sides here are going to have to use up my fence. I'm going to try to use all my fence so I can make it larger. I'm not going to leave some out. But just thinking about a way to start this, I'm trying to maximize my area. So eventually I'm going to want to write a formula for the area of this rectangle. I'll call it L and W. There we go. I'd like to maximize length times width. Kind of like the 2a squared plus b squared. This isn't particularly useful. It's kind of a structure for a function, but we need a function of one variable. But also, like last time, L and W can't be just anything under the sun. There's some restrictions on their size, and they're related to one another also. All right, so neither one can be smaller than 4. So L and W both have to be greater than or equal to 4. And also, well, let's see. Like for instance, just as an example, let's say that I said, well, what if L is 10? I know the lengths of the other two sides automatically, right? This one would also be 10 if this is a rectangle. And then I'm trying to use all of my fence. So I'd have 20 feet used, I'd have 64 feet left. I mean, it doesn't have to look this way. I could have it narrow the other way instead. But I could have something, and maybe it's this way, or maybe more squarish. And thinking about length and width, maybe this is like 30. And then this side's 30. And then that's 60 feet out of the 84 used. So there's only 24 left for this. But whenever you know one length, or pick a length for one of the three sides, you know the other two automatically. So there's no need to have, well, certainly don't need to have 3 different letters. We only had 2 in the first place. But we should be able to write an expression for the area or label these sides using just a single letter, because whatever I pick for L, that's going to be this other side too. The width is going to be the total length of fence minus whatever those 2 L sides were, length. And you could call them X and Y instead of W and L. That obviously doesn't matter. But if I use L and 84 minus 2L because there's 2 of those that are the same length that we subtracted. You can see we subtracted 2 10s here, we subtracted 2 30s there. Whatever you would do with specific examples of numbers, you can do in general for any value of L also. If this side's L and so is that, then 84 minus 2 L's is what's left for the third side. So my area, instead of L times W, I could have, I don't need to do L times W, still just length times width, but 84 minus 2L, or maybe I'll make this more legible here. Let me call it X instead, because L's, I drew them like that so they didn't look like 1s, but they kind of look like E's. So X times 84 minus 2X. It's a quadratic function with a negative 2x squared leading term if you were to multiply it out. If I were to graph it, I know it's a parabola with vertex at the top. I'm trying to maximize. That's a good sign. It's probably going to be that vertex, but I have to keep in mind my domain. So we know length and width both have to be greater than 4, which in terms of x here, I would need x to be greater than or equal to 4. And I'd also need this, which is the width, 84 minus x, or 84 minus 2x, to be greater than or equal to 4, which would be, what, 80 is greater than or equal to 2x. So x is less than or equal to 40. 40 is greater than or equal to x. So x is between 4 and 40, in other words. So converting this into a single letter, using x or whatever this is, between 4 and 40. And that is a 40. I don't know why this keeps kind of making extra lines. There. 4 through 40 is my domain. So thinking about parabolas and graphs, as long as that vertex is between 4 and 40, that's my maximum. I don't care about a minimum here. I'm not trying to minimize my storage space. That would be a silly thing to do. So I'm going to take a look at my critical value here. That's in the, I hope, in the middle of 4 and 40. If it's not, I'll check 4 and I'll check 40 to see which one gives me the maximum area. So a of x or a of L or whatever letter you chose, its derivative should be pretty simple. You can do a product rule or just, oh, this is 84x minus 2x squared. Easy enough to multiply out. So the derivative of 84x minus 2x squared would be 84 minus 4x. And this has 1, 0. It's not undefined anywhere. It's equal to 0, indicating a flat spot. And I know this is a parabola, so this would be the vertex at the place where it's 0. So 84 is 4x, and so x is 21, which is in our interval, meaning just kind of combining graphing knowledge with calculus so as to not, you can avoid some algebra work and some substituting if you know a little bit about graphs mentally. If I was graphing a of x, let's see, I only care about it between 4 and 40. The vertex is at apparently 21. So whatever on earth it looks like elseways, this is certainly the maximum. The maximum is not going to happen at those endpoints at 4 or at 40, which would be slightly before the intercepts. The maximum is going to happen when x, there's what was L here, when x is 21. So this x, which I had previously as L, that gives me the best options here. This is 21 on each of these two sides. And you see, oh, 21 and 21, that's 42, leaving 42 for this other dimension. So it's really a 21 by 42 enclosure, and we could find the area of that, 41, 882, I believe. But this is with a 21 by 42 foot enclosure, 42 parallel to the house. Not two sides of 42 and one that's 21. It's two sides of 21 and one of 42, so that adds up to 84. We want a 21 by 42 foot enclosure, and that's, what did I say, 882 square feet. That's our ideal situation, or to optimize our storage space, we should construct a 21 by 42 foot enclosure, and that gives us 882 square feet of storage. So looking at some of the other examples up here, like this 10 by 64, notice that's 640 square feet, that's less. Or this 30 by 24, let's see, I think it's 720 square feet, also less. You can try a bunch of other numbers and make sure that they are actually coming out less, kind of as a way to double check that you didn't really mess up and write something completely wrong. There's multiple steps to this, including creating the function you're dealing with in the first place. So just graphing it isn't necessarily going to help you check your work, but certainly do graph your function and see that the maximum is where you think it is, and that the endpoints aren't of consequence if you thought that they weren't. But let's do one more. Let's see, maybe. There we go. All right, so another geometric-based one. So next week we're going to do a couple that involve some trigonometry. So reading assignment over the weekend is to look at chapter 2, specifically remembering the relationship between sine and cosine and unit circles and opposites, adjacents, triangles. Those sorts of things can help you relate angles and lengths to one another, whether they fit in a triangle, a right triangle, or just in a circle. But in any case, a square-based box-shaped shipping crate, so just standard box, but boxes could be pyramid-shaped or anything else. So what you think of normally when you think of a box, regular box, is supposed to have a volume of 16 cubic feet. The material used to make the base is thicker, maybe, costs twice as much per square foot as the material in the sides, and the material for the top costs half as much as the material in the sides. So we don't have actually any costs specifically here, but just relative costs. We want to know what dimensions should we make this crate have, length, width, and height, so that it'll hold 16 cubic feet, and so that the cost will be as small as possible. We're not going to be able to determine what that cost is because we don't have any numbers for it. But we'll be able to determine, regardless, how to minimize the cost based on the relative costs of the different surfaces of this box. Take a little bit, see if you can maybe sketch a box. Think about how you'd calculate the cost, if you knew it, per square foot. But notice also that it's a square-based box, meaning 2 of the 3 dimensions are the same number. So this is not going to be a parabola. So there's a lot of kind of unknowns here. I don't really know what the prices are, but there's 3 different price per square feet that we're going to use. If you want to make up a number, in reality, you can make up a number to be the price per square foot for the top, sides, and bottom, as long as they fit the pattern. And you should get the same result, but just with more numbers. But the base costs the most, the sides cost the medium amount, the top costs the least per square foot. But let's say that we had dimensions, let's see, Since the base and the top are squares in this is x by x, and then I'll call this other dimension y, since it doesn't have to be the same. Might end up being the same. But what I do know about this is that x and y aren't independent, because the volume is supposed to be 16 cubic feet. So x times y would have to equal 16, or in other words, I don't have to use a y, I can use 16 over x squared for that height. Thinking about domain, it doesn't really say anything here, but I know that dimensions for box lengths should probably be something positive. 0 wouldn't even be a good idea, and in fact, if one of them is 0, you're never going to get a volume of 16. So greater than 0 is all we really know for x or y, either one, but in the end, just I have to use positive values of x. It's not a very specific domain. It's only going to have, well, no endpoints, just probably first quadrant sorts of parts of a graph that I'd be concerned with. A graph of what? Graph of cost. Because I'm trying to minimize my cost, I'd like to have a function whose output is cost and whose input depends on all the different details in the problem. So let's say that just relative, I'm just going to make up a symbol for the cost per square foot. So the sides are kind of in the middle. Let me say that that's P as the price per square foot. The bottom is twice as much, so that would be 2P, and the top is half as much per square foot. Let's say that the price per square foot is 1/2 P for the top. You could also do like 1, 2, and 4, or whatever. Certainly don't have to use the symbol P, but I don't know what the price per square foot is, so I'm just going to make up a symbol to represent that. Because I know that the cost of the base, for instance, if I knew how big the base was, I'd multiply the number of square feet in the base by the price per square foot for the base, and that should give me the overall cost. So for the base here, whatever 2P is times x squared. P isn't a variable, P is just a parameter standing for this, apparently the price per square foot for the sides. Now the cost of the 4 sides, each of the 4 sides, these vertical in this picture, are x by y, otherwise known as x by 16 over x squared. And x times 16 over x squared reduces to 16 over x, okay? So that's the area of the sides. If I want to know the cost for 4 sides that are each this big, it'd be 64 over x, 4 times this, times p. I'm just going to put the p in front. P times 64 over x. 4 of these. So 4 sides would be that times 4. Take it over 1, makes 64 over x. And then the cost of the top surface is the least expensive. Its area is just like the bottom, it's x squared, but its cost per square foot is only 1/2 p. So number of square feet times cost per square foot, and we have an expression for our cost. Where x is a variable, p is just a parameter. If you want to factor it out, you can. It'd just be a constant multiple in terms of finding a derivative. But maybe making this a little bit less messy, I can see I've got, let's see, 2px squared and 1/2 px squared. So that's 2.5 or 5/2 p x squared. And then I've got this other, I'm going to write this with an exponent, 64p x to the negative 1. So there, that looks a lot less awful. Now, that takes a lot of work to get to that point. It's a lot of planning and plotting, thinking about volumes of boxes, thinking about surface areas of boxes, cost per square foot, and relative cost per square foot, in fact, and combining some coefficients and like terms and rewriting things in exponent form. But now that it's there, keeping in mind that x is only going to be something positive, if I want to find a maximum of, or a minimum of this, I'm like, well, I have no idea what shape this is. This is a weird one. It's got a quadratic term and a reciprocal x term. So has a vertical asymptote at 0 and something else. Don't worry about trying to come up with the graph of it mentally. You can graph it on a graphing calculator, but the derivative of this would just be 5p times x. Remember, p is just some number. So just like the 5/2 is multiplied onto this x squared, p is multiplied on also. So derivative of the first term, derivative of the second term, negative 64p x to the negative 2. I'd be interested in knowing when this is undefined or when it's 0. Now it's undefined only at x equals 0, which isn't in our domain. It's the vertical asymptote of the cost function, even if we were using it. It might equal 0, but it's kind of hard to tell where. So messy algebra, don't forget some of your algebra from years gone by. That is not the blue that I wanted. There we go. But if I want to know when 5px, for what values of x, p isn't a variable, and I'm just going to write minus 64p x to the negative 2. I want to know when that equals 0, because that's going to be a flat spot on my graph, if nothing else. We can investigate. But keep in mind that p is a constant. So I could factor this out, because in terms of finding derivatives of things with powers of x in them, usually factoring is a thing that we do. So 5x minus 64x to the negative 2. If you want to factor out x to the negative 2, we can do that. We could also write this as like in fraction form and do more kind of cross-multiplying stuff. But keep in mind that if two things multiply to make 0, then one of them has to be 0, and I bet it's not p. You're not getting free product. So it's this part that has to be 0. So we'll figure out what values x must have to make this equal 0. And again, you can either factor out, like x, the lowest power of x, x to the negative 2, which would get rid of this and give us x cubed here. 5x cubed minus 64, which maybe that looks more normal. I know that this part isn't going to be 0 because that's 1 over x squared, not equal to 0. So maybe this is. And this looks more like a normal sort of algebra equation. 5x cubed minus 64. When is that equal to 0? Oh, the kind of subtract and divide sort of solving. This one involves a cube root. And in fact, to solve this, 5x cubed equals 64. So x is going to be the cube root of 64 over 5, which, what is that? 12.8 cube root? Don't really know what that is. 2 point something. But thinking about this, from here, this algebra is a little messy, but none of it would have been able to be done without finding our cost function in the first place. If you want to graph something, we can't graph it with the p in there, but if you want to graph it and see what's going on, we can factor out the p and just realize that all that would do is scale this up by a certain factor, or change what the actual cost is, but not the relative where the highs and lows of the cost are. So let me just, let's see, pull up graphing calculator here. I'm gonna, oops, not that. Delete this while I can still see the other function there. So I'm gonna write, I'm gonna define my c of x without p in it, just because that's just gonna be a scalar factor. I don't know what p is. I could define a parameter p and put the p in it as it was. But, oh, actually what I want is c of x. I was gonna say I can graph the derivative also. But we'd have 5/2, if I can type right, 5/2 x squared. Sorry, I'm just using my scratch work here, plus 64x to the negative 1. All All right, I'm going to clear all this off and take a look at this graph. So this one. I can see that when x is greater than 0, there's a minimum cost that occurs right around here in terms of like clicking on values, like, all right, looking at the y values, 41.4, 3, 2, 1, 0. It's right around here, 0394. That's the lowest spot that I can get. This 2.33921, I bet that's a cube root of 65 over, or 64 over 5, whatever that was, which was the minimum we had. Now the y value here, this would be if p equals 1. If p equals 2, let's multiply the whole thing by 2. If p equals 3, multiply the whole thing by 3, or whatever p is. That would just scale this up. Like I said, with the way the problem was given, we can't actually find specific costs, just relative costs, but the minimum and maximums that would occur within any restricted domain would all be at the same places or for the same values of x. So regardless, our container should be constructed where x is the cube root of 64 over 5, and y is whatever 16 divided by that is. So cube root of, let me do it this way, let's see, root, do it the old-fashioned way, 64 over 5 to the 1/3 power, 2.33921. And so 16 divided by that, copy and paste, oops, would be 1.25 for the other dimension. So 2.34 approximately by 2.34 by 1.25 would be your 16 cubic foot shipping container with the minimum cost, regardless of precisely what that cost is. It's based on knowing that relative cost between the sides and the bases and the tops. But, so we saw this involved a bit of geometry. If you take a look ahead, note that your next several homework assignments, you should be able to work on several of them. The next one that's due is just about increasing versus decreasing and first and second derivatives and stuff. Then there's another one about plain old things like the j of x example we did at the start of class, just find the critical values and that's it. The third one after that is going to have problems like this where there's some geometry involved or some other basic setups like cost, like we used here, to write a function that you're trying to optimize. There's another one with some harder that involves some trig that's after that, but we'll do some trig on Tuesday. I will see you next week. For those of you that had lab 4 to 7 last night and have a makeup, come see me.